What if I told you that time actually slows down the faster you move? And no, this isn't science fiction. This is real physics. And it all comes from one single number. Tonight, we're going to talk about something that sounds simple but turns out to be one of the strangest, most mind-bending concepts in all of physics. The speed of light. You have probably heard this number before. 186,000 miles per second. Scientists throw this number around constantly when they talk about the universe. But here is what most people never realize. When you truly understand what the speed of light means, not just as a fast speed, not just as some number that Einstein used in his equations, but as a cosmic speed limit built into the very fabric of reality itself, it completely changes how you see the universe. The consequences of that speed limit are so strange, so deeply counterintuitive, that they challenge our basic ability to make sense of the world around us. By the end of this journey, you are going to understand why time slows down for moving objects, why space itself shrinks, why two people can disagree about whether two different events happen at the same exact moment, and both of them be completely correct, and why, no matter how advanced our technology becomes, we may never be able to visit even the nearest stars within a single human lifetime. Let that sink in for a moment. Time slowing down, space shrinking. The same event happening at different times for different people. This is not metaphor. This is how the universe actually works. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now, let's dive in. For most of human history, people assume that light traveled instantaneously, and honestly, that makes perfect sense based on everyday experience. When you flip a light switch, the room illuminates immediately. There's no delay that you can perceive. When lightning strikes during a storm, you see the flash right away. The thunder takes time to reach you, sure, but the light appears the very moment the bolt strikes, so it seemed completely obvious that light must travel infinitely fast. It just arrives. The ancient Greek philosopher Empedocles, who lived around 490 to 430 BCE, was one of the first people to question this assumption. He proposed that light was something in motion, and therefore must take some time to travel from place to place. But his contemporary, Aristotle, dismissed this idea entirely. Aristotle argued that light propagation was instantaneous, and because Aristotle's word carried enormous weight in Western thought for over 2,000 years, his view dominated. If Aristotle said light was instantaneous, then light was instantaneous. Case closed. In the Islamic world, the scholar Al-Hazan, also known as Ibn al-Haytham, proposed in his 1021 work called the Book of Optics that light takes time to travel from one place to another and moves at different rates through different materials. This was remarkably insightful for its time. But without any way to actually test this idea, it remained just speculation. You can have the right answer, but without evidence, it is just a guess. The first person to actually attempt measuring the speed of light was Galileo Galilei. In his 1638 book, Two New Sciences, Galileo described an experiment that sounds almost comically simple. Two observers would stand on distant hilltops near Florence, each holding a covered lantern. The first observer would uncover their lantern, and the moment the second observer saw the flash, they would uncover theirs. By measuring the time between uncovering the first lantern and seeing the return flash, Galileo hoped to calculate how long light took to travel the round trip. Galileo tried this at distances of less than 1 mile. He detected no delay whatsoever. He correctly concluded that light is, if not instantaneous, extraordinarily rapid. But here is why the experiment was doomed to fail from the start. Light travels 1 mile in approximately 5 microseconds. That is 5 millionths of 1 second. Human reaction time, however, is around 200,000 microseconds. Think about what that means. The delay Galileo was trying to measure was 40,000 times smaller than the error introduced by human reflexes. It was like trying to measure the weight of a single grain of sand using a bathroom scale. The tool simply was not sensitive enough for the measurement. Other scientists repeated Galileo's experiment with the same null result. Measuring the speed of light would require something other than human reflexes. It would require looking much, much farther away. It would require astronomical distances. The breakthrough came from an unexpected source, the moons of Jupiter. Ole Rømer was a Danish astronomer born on September 25, 1644. In the 1670s, he was working at the Paris Observatory under the famous astronomer Giovanni Cassini. Rømer's job was to create precise tables predicting when Jupiter's moon, Io, would disappear behind Jupiter. These events, called eclipses, happened with clockwork regularity. They were useful for navigation, and accurate predictions were valuable to sailors trying to determine their longitude at sea. But as Rømer compiled his observations over months and years, he noticed something strange. The eclipses were not happening exactly when predicted. When Earth was moving toward Jupiter in its orbit, the eclipses seemed to occur slightly early. When Earth was moving away from Jupiter, they occurred slightly late. Over the course of a year, these timing differences accumulated into a significant discrepancy. Rømer realized there was only one explanation that made sense. Light takes time to travel. When Earth was closer to Jupiter, there was less distance for the light to cross, so observers saw the eclipses sooner. When Earth was farther away, the light had to travel a greater distance, causing delays. The eclipses themselves were happening like clockwork, but the light carrying news of those eclipses had to cross different distances depending on where Earth was in its orbit. Think about what Rømer was realizing. He was not seeing the eclipses as they happened. He was seeing them after a delay that depended on distance. It was like watching fireworks from across a valley and noticing that the sound arrives later than the flash. Except here, even the flash was delayed. The light itself needed time to cross the vast gulf of space. On August 22, 1676, Cassini announced to the Academy of Sciences that future eclipse predictions would incorporate corrections for light travel time. Then in September of that year, Rømer made a bold prediction. He calculated that the eclipse of Io scheduled for November 9th would occur 10 minutes later than the standard tables predicted. Think about how audacious this was. Rømer was essentially saying, I know when this eclipse will happen better than the official predictions, and the reason is that light takes time to travel. If he was wrong, he would look foolish. If he was right, he would have proven something fundamental about the nature of light. On November 9th, 1676, astronomers watched and waited. The eclipse occurred at 5:35 and 45 seconds in the morning, exactly 10 minutes late, precisely as Rømer had predicted. On November 21st, Rømer presented his findings to the French Academy of Sciences. On December the 7th, his work was published. This was the first successful measurement of light speed in human history. Rømer estimated that light takes about 22 minutes to cross the diameter of Earth's orbit around the Sun. This gave him a speed of approximately 140,000 miles per second. He was off by about 24 to 25%, mainly because astronomers at the time did not know the precise size of Earth's orbit. But he had proven what Aristotle got wrong. Light does not arrive instantly. It races across space unimaginably fast, but it still takes time to get where it is going. It would take 53 years for independent confirmation. 53 years before someone else proved Rømer right through a completely different method. In 1728, English astronomer James Bradley discovered something called stellar aberration. While searching for a completely different phenomenon, Bradley was trying to detect the slight shift in star positions caused by Earth orbiting the Sun, something called stellar parallax. This was an important measurement because it would provide direct evidence that Earth actually moved around the Sun, something that was widely accepted but still not proven by direct observation. What Bradley found instead was that stars appeared to shift position by about 40 arcseconds over the course of a year, but in the wrong direction and at the wrong timing for parallax. The stars seemed to be displaced in the direction Earth was moving at any given moment. The explanation came, legend says, while he was sailing on the Thames River. Bradley noticed that the direction of the wind relative to his boat seemed to change when the boat changed direction, even though the actual wind had not shifted. He realized stars behaved the same way. Picture yourself walking through a snowstorm. Even if the snow is falling straight down, you have to tilt your umbrella forward to stay dry because you are moving into the falling snow. Starlight does the same thing. It appears slightly displaced in the direction of Earth's orbital motion. This phenomenon only makes sense if light takes time to travel. If light arrived instantly, there would be no aberration. The fact that aberration exists and has a specific measurable angle allowed Bradley to calculate light's velocity. By measuring this displacement and knowing Earth's orbital speed, Bradley calculated light's velocity at between 183,000 and 187,000 miles per second. He was within 2% of the modern value, and he had independently confirmed what Rømer discovered half a century earlier. Light has a speed, and that speed, while almost unimaginably fast, is finite and measurable. The next major advance came from trying to measure light speed here on Earth without relying on astronomical distances. This was the challenge that had defeated Galileo. How do you measure something that travels 1 mile in 5 millionths of a second using equipment you can set up in your local area? Armand Fizeau was a French physicist born on September 23, 1819. On July 23, 1849, he performed an elegant experiment and announced the results to the Academy of Sciences in Paris. Fizeau set up a light source on a bell tower in Suresnes, a suburb west of Paris. About 5.4 miles away on Montmartre Hill, he placed a mirror. Between the light source and the mirror, he positioned a toothed wheel with 720 teeth. Here is how it worked, and it is genuinely clever. Light from the source passed between 2 teeth of the wheel, traveled to the distant mirror, bounced back, and returned to the wheel. If the wheel was not spinning or was spinning slowly, the returning light would pass back through the same gap and reach the observer's eye. But if the wheel was spinning at just the right speed, by the time the light returned, the wheel would have rotated enough that a tooth blocked the path. The light would be cut off. By carefully adjusting the wheel's rotation speed, Fizeau could find the exact speed where the returning light was blocked, and then the speed where it passed through the next gap. He found that at 25.2 rotations per second, the returning light passed through the next gap over from where it started. From this, knowing the wheel's rotation speed, the number of teeth, and the total distance the light traveled, he could calculate light's velocity. His result was about 194,600 miles per second. This was about 4.5% too high, but it was a triumph nonetheless. For the first time, light speed had been measured without relying on the vast distances of the solar system. The cosmic could be measured in a laboratory. Galileo's dream had finally been achieved. 2 centuries after he first proposed the experiment, Fizeau's former collaborator and rival, Léon Foucault, developed an even more refined technique using rotating mirrors instead of toothed wheels. In 1862, Foucault measured light speed at about 185,000 miles per second. This was only 0.6% different from the modern accepted value, remarkably precise for equipment built over 160 years ago. But Foucault had done something even more important 12 years earlier. On April 27, 1850, he demonstrated that light travels slower in water than in air. This might seem like a minor detail, but it was actually decisive evidence in one of physics' longest-running debates. Isaac Newton had proposed that light consisted of tiny particles, which he called corpuscles. According to Newton's theory, light should travel faster in denser materials like water, because the particles would be pulled in and accelerated. The competing wave theory predicted the opposite. Light waves should slow down in denser media, just as sound waves behave differently in different materials. Foucault's 1850 experiment showed conclusively that light travels slower in water. As one historian put it, this result drove the last nail in the coffin of Newton's particle theory of light. Light behaved as a wave. Newton, for all his genius, had gotten this one wrong. Even the greatest minds can be mistaken. The quest for ever greater precision led to Albert Abraham Michelson, an American physicist born on December 19, 1852. Michelson's family immigrated from Prussia when he was 2 years old. At 17, he received an appointment to the United States Naval Academy directly from President Ulysses S. Grant. Michelson became obsessed with precision measurement. In 1878 and 1879, while stationed at the Naval Academy in Annapolis, Maryland, he refined Foucault's rotating mirror technique and obtained a value of about 186,350 miles per second. This was the most accurate measurement of light speed in history up to that point. But Michelson's most famous experiment was not about measuring how fast light travels. It was about measuring something that turned out not to exist at all, and this experiment would accidentally pave the way for the most revolutionary theory in the history of physics. In the late 19th century, physicists believed that light waves, like sound waves, needed a medium to travel through. Sound requires air or water or some physical substance to propagate. You cannot hear anything in a vacuum because there is nothing for the sound waves to travel through. So what did light waves propagate through? What carried them across the emptiness of space from the sun to Earth? Scientists proposed the existence of a substance called the luminiferous ether, an invisible, weightless material that filled all of space and carried light waves the way air carries sound. This ether had to have peculiar properties. It had to be rigid enough to transmit waves at enormous speed, yet fluid enough not to impede the motion of planets through it. It had to be everywhere, filling all of space, yet completely undetectable by any ordinary means. If the ether existed, and if Earth moved through it as our planet orbited the sun, then light should travel at slightly different speeds depending on direction. Light traveling in the direction of Earth's motion through the ether would be swimming against the current, so to speak, and should arrive slightly slower. Light traveling perpendicular to Earth's motion would not face this resistance. The difference would be small, but with sensitive enough equipment, it should be detectable. Michelson designed an instrument called an interferometer to detect this difference. The device split a beam of light into two perpendicular paths, bounced each beam off mirrors, and recombined them. If one path was faster than the other, the recombined beams would be slightly out of sync, creating an interference pattern that could be measured with extreme precision. In 1887, Michelson teamed up with Edward Williams Morley, a chemistry professor at Western Reserve University in Cleveland, Ohio. They set up the experiment in the basement of a dormitory. To isolate the apparatus from vibrations, they mounted the interferometer on a large sandstone slab floating in a pool of mercury. The effective path length was about 36 feet, achieved through a complex arrangement of 16 mirrors. The experiment used monochromatic yellow light from a sodium lamp with a wavelength of about 589 nanometers. Based on their calculations, they expected to see a fringe shift of approximately 4/10 of one fringe as they rotated the apparatus to different orientations. This would be clear evidence of Earth's motion through the ether. From April through July of 1887, with key observations on July 8th, 9th, and 11th, Michelson and Morley conducted their measurements. The result was essentially nothing. The measured displacement was less than 1/400th of what they expected. In August 1887, Michelson wrote to the British physicist Lord Kelvin with the words, "The result is decidedly negative." Yes, you heard that right. They set out to prove the ether existed, and they proved it didn't. This is often called the most famous failed experiment in scientific history. Michelson and Morley had set out to measure Earth's motion through the ether, and instead proved that the ether did not exist, or at least did not affect light the way everyone assumed. Light traveled at exactly the same speed in every direction, regardless of Earth's motion through space, no matter which way you pointed your apparatus, no matter what time of year, no matter how carefully you measured. Light always traveled at the same speed. For his precision optical instruments and the investigations they enabled, Michelson received the Nobel Prize in December 1907. He was the first American to win the Nobel Prize in any science. The Michelson-Morley experiment had raised a deep puzzle. If there was no ether, what carried light waves? And why did Earth's motion not affect light speed? The answer would require completely rethinking our understanding of space and time. It would require a revolution. Take a breath, because it gets even stranger. In October 1983, the 17th General Conference on Weights and Measures made a decision that would have seemed absurd to earlier generations of scientists. They stopped trying to measure the speed of light. Instead, they defined it. The official definition fixed the speed of light at exactly 186,282.397 miles per second with zero uncertainty. By definition, the meter is now derived from the speed of light, not the other way around. This might seem like cheating, but it actually makes deep sense. After centuries of ever more precise measurements, scientists had come to understand that the speed of light is not just a number we measure. It is a fundamental constant of nature woven into the fabric of spacetime itself. It made more sense to use this constant as a foundation for other measurements than to keep trying to pin it down more precisely. The speed of light in a vacuum is now as exact as the number of eggs in a dozen. It is not something we measure anymore. It is something we know. Now we arrive at the moment when everything changed. In 1905, a 26-year-old man working at the Swiss Patent Office in Bern published 4 papers that transformed physics. His name was Albert Einstein, and he had no university position, limited access to scientific reference materials, and no laboratory. He called the patent office that secular cloister where I hatched my most beautiful ideas. Einstein's main intellectual companion was a colleague named Michel Besso. Einstein later wrote that he could not have found a better sounding board for his ideas in all of Europe. They would walk home together after work discussing physics, debating ideas, working through problems. And from these conversations, some of the most important insights in scientific history emerged. The year 1905 is known as Einstein's Annus Mirabilis, or Miracle Year. The 4 papers he published in the German journal Annalen der Physik addressed completely different topics, and any one of them would have secured his place in scientific history. The first paper, received on March 18th and published on June 9th, explained the photoelectric effect and proposed that light comes in discrete packets of energy, which we now call photons. This work would eventually win Einstein the Nobel Prize. The second paper, received on May 11th and published on July 18th, provided mathematical proof that atoms exist by explaining the random motion of tiny particles suspended in liquid, called Brownian motion. The third paper, received on June 30th and published on September 26th, was titled On the Electrodynamics of Moving Bodies. This 31-page paper introduced the special theory of relativity. It would eventually overturn our understanding of space, time, and causality. The fourth paper, received on September 27th and published on November 21st, was just 3 pages long, but contained perhaps the most famous equation in science. In it, Einstein showed that mass and energy are equivalent, related by a factor of the speed of light squared. Think about what Einstein accomplished that year. He was 26 years old. He had no academic position, no laboratory, no research assistants. He worked 6 days a week examining patent applications for inventions, and in his spare time, during evenings and weekends, he rewrote the foundations of physics. 4 revolutionary papers in a single year. Any one of them would have made him famous. Together, they made him immortal. Let us focus on that third paper, because it is the one that explains why the speed of light breaks reality. Einstein had been troubled by a thought experiment since he was about 16 years old, sometime around 1895 or 1896. He described it decades later in his autobiographical notes written in 1946. A paradox upon which I had already hit at the age of 16. If I pursue a beam of light with the velocity c, I should observe such a beam of light as an electromagnetic field at rest, though spatially oscillating. There seems to be no such thing, however, neither on the basis of experience nor according to Maxwell's equations. Think about what Einstein was imagining. A teenager picturing himself running alongside a beam of light, matching its speed, looking over at the light to see what it looked like. If he could do that, what would the light look like? According to Newton's physics, he should see a frozen wave, a stationary ripple in the electromagnetic field just sitting there next to him as they traveled together through space. But James Clerk Maxwell's equations describing electromagnetism did not allow for such a thing. Maxwell's equations predicted that electromagnetic waves, including light, must always travel at a specific speed. Frozen light, stationary light, light moving at any speed other than the speed of light simply was not physically possible according to these equations. This paradox nagged at Einstein for years, a decade of wondering thinking turning the problem over in his mind. The solution he eventually reached was radical. Maybe the premise was wrong. Maybe it was not possible to run alongside a beam of light at all. Maybe light always travels at the same speed relative to any observer, no matter how fast that observer is moving. Einstein built his special theory of relativity on 2 fundamental assumptions or postulates. The first postulate, which he called the principle of relativity, states that the laws of physics are the same in all inertial reference frames. An inertial reference frame is just a viewpoint that is not accelerating. If you are on a smoothly moving train with the windows covered, no experiment you perform inside the train can tell you whether you are moving or stationary. All motion is relative. There is no absolute state of rest. There is no cosmic background against which motion can be measured. There is only motion relative to other objects. The second postulate states that light always propagates in empty space at the same definite velocity, regardless of the motion of the light source or the observer. Whether you are moving toward a light source or away from it, whether the source is moving toward you or away from you, you will always measure light traveling at exactly the same speed, 186,282 miles per second. These 2 postulates seem almost reasonable when stated individually. The first one had been around since Galileo. The second one was essentially what the Michelson-Morley experiment had shown. But together they have consequences that violate everything we think we know about how the world works. Consider this situation. You're on a train moving at half the speed of light. That is about 93,000 miles per second. You turn on a flashlight and shine it toward the front of the train. Common sense says that from the perspective of someone standing on the platform watching the train pass, that light beam should be traveling at 1.5 times the speed of light. The train speed plus the light speed. That is how velocities add, right? If you're on a bus going 50 miles per hour and you throw a ball forward at 20 miles per hour, someone on the sidewalk sees the ball moving at 70 miles per hour. Speeds add. But Einstein's second postulate says no. The person on the platform will measure that light traveling at exactly the speed of light. Not 1.5 times, just the speed of light. The same speed you measure on the train. How can this possibly be true? How can both you on the train and the observer on the platform measure the same beam of light traveling at the same speed when you are moving at half the speed of light relative to each other? The answer is that time and space themselves must be flexible. If the speed of light is absolute and constant for all observers, then time and space must adjust to make this possible. Different observers experience time passing at different rates. Objects in motion shrink in the direction they are traveling. Events that one observer sees as simultaneous may not be simultaneous to another observer. This is not a flaw in our measuring instruments. It is not something going wrong. Time and space genuinely behave this way. And once you accept Einstein's two postulates, all of these strange consequences follow mathematically, inevitably, inescapably. The fourth paper Einstein published that year dealt with the relationship between mass and energy. It carried the unassuming title, "Does the inertia of a body depend upon its energy content?" In just 3 pages, Einstein demonstrated that mass and energy are two forms of the same thing. The famous equation we know as E equals mc squared did not actually appear in that form in the paper. Einstein wrote it differently, using L for energy and V for the speed of light. If a body gives off the energy L in the form of radiation, its mass diminishes by L divided by V squared. The implications are staggering. Mass can be converted into energy. Energy can be converted into mass. And because the speed of light squared is such an enormous number, approximately 9, followed by 16 zeros in standard metric units, a tiny amount of mass contains an almost inconceivable amount of energy. Think about what this means in concrete terms. 1 pound of matter, if completely converted to energy, would release about 40 quadrillion joules. That is roughly equivalent to a 10 megaton nuclear explosion. The mass of a paperclip completely converted could power a city. The energy was there all along, locked inside the mass, waiting. This equation explains why the sun shines. Deep in the sun's core, hydrogen atoms fuse to form helium. The helium weighs slightly less than the hydrogen that made it. Where does that missing mass go? It becomes energy, radiating outward as the sunlight that warms our planet. The sun is slowly converting its mass into energy, about 4 million tons every single second, and will continue doing so for billions of years. The equation also explains nuclear power and nuclear weapons. When heavy atoms like uranium split apart, or when light atoms like hydrogen fuse together, a tiny fraction of their mass converts to energy. The atomic bomb dropped on Hiroshima converted less than 1 gram of matter into the blast that destroyed a city. Less than the mass of a paperclip. Einstein himself was not involved in building the atomic bomb. When the Manhattan Project was underway in the 1940s, he was denied security clearance. But his equation revealed the possibility that was always there, hidden in the relationship between mass and energy. Now, let us dig into exactly how the speed of light breaks our understanding of reality. This is where things get genuinely strange. These are not speculative ideas or theoretical possibilities. These are measured facts, confirmed by countless experiments over the past century. The universe actually works this way, whether or not it makes intuitive sense. The first consequence of Einstein's theory is called time dilation. When an object moves relative to you, its clock runs slower than yours. Not appears to run slower. Actually runs slower. Let me say that again because it is important. A moving clock ticks more slowly than a stationary clock. This is not an optical illusion. It is not a mechanical problem with the clock. It is not a measurement error. Time itself passes more slowly for moving objects. The mathematical formula for this involves something called the Lorentz factor. At everyday speeds, it is essentially equal to 1, meaning time passes normally. But as speeds approach the speed of light, the Lorentz factor grows without limit. Let me give you concrete numbers so you can really feel what this means. At 50% of light speed, about 93,000 miles per second for every year that passes on Earth, only about 10.5 months pass for someone traveling at that speed. Not much of a difference in everyday terms, but measurable. At 90% of light speed, 1 year on Earth corresponds to less than 5.5 months for the traveler. Now we are seeing significant time differences. At 99% of light speed, 1 Earth year equals only about 52 days for someone moving that fast. More than 6 years worth of Earth time compresses into a single year for the traveler. Push even closer, to 99.999% of light speed, and a single Earth year shrinks to just 12.5 hours on the moving ship. The pattern is clear. The faster you go, the more time bends. This is not science fiction. This is measured reality, verified countless times in laboratories around the world. The clocks on GPS satellites, the particles in accelerators, the decay rates of cosmic ray muons, all of them confirm that time dilation is real. To truly grasp how fundamental time dilation is, consider a simple thought experiment called the light clock. Imagine a clock that works by bouncing a beam of light between two mirrors. Each time the light makes a round trip, the clock ticks once. If the clock is stationary relative to you, you see the light traveling straight up and down between the mirrors. But now imagine that clock is moving sideways relative to you at high speed. From your perspective, the light is not traveling straight up and down anymore. It is traveling in a diagonal zigzag pattern because each time it bounces, the mirrors have moved to a new position. The diagonal path is longer than the straight vertical path, but light always travels at the same speed. So if the path is longer, the journey takes more time. Each tick of the moving clock takes longer than each tick of a stationary clock. This is not a peculiarity of this particular clock design. Any physical process that can be used to measure time will show the same effect. Chemical reactions, biological aging, radioactive decay, the vibration of atoms, all of these slow down for moving objects. Time itself is slower. Not just clocks, time. The second major consequence is length contraction. Objects moving relative to you are physically shorter in the direction of their motion. This is not a visual illusion caused by light travel time. The object genuinely occupies less space. At 50% of light speed, an object contracts to about 87% of its rest length. At 87% of light speed, it contracts to half its rest length. At 99% of light speed, it is compressed to about 14% of its original length. At 99.99%, it is down to about 1.4%. Consider the Stanford Linear Accelerator in California. It is a straight tube about 2 miles long. Inside, electrons are accelerated to very close to the speed of light. From the electron's perspective, because of length contraction, the entire accelerator appears to be only about 20 inches long. The electrons experience themselves as passing through a tunnel shorter than your arm span, even though, from our perspective, the tunnel is almost 2 miles long. The electrons genuinely experience a shorter tunnel. From their perspective, the tunnel really is only about 20 inches long. This is not a calculation convenience or a theoretical abstraction. It is what actually happens. The universe does not privilege one viewpoint over another. There is a famous thought experiment called the ladder paradox, or the barn paradox, that illustrates how strange this gets. Imagine a ladder that is longer than a barn. Someone runs through the barn carrying the ladder at relativistic speed. From the barn's perspective, the ladder contracts, and for a brief moment, the entire ladder fits inside the barn with both doors closed. But from the ladder carrier's perspective, the barn is contracted, not the ladder. So the ladder should not fit at all. Surprisingly, the universe allows both versions of events to be true. The resolution involves the relativity of simultaneity, which we will discuss next. What one observer sees as simultaneous, both doors closed at the same moment, is not simultaneous for the other observer. The universe remains consistent, but only if we abandon the idea that there is a single, universal now. The third consequence may be the strangest of all: the relativity of simultaneity. Events that happen at the same time for one observer may not happen at the same time for another observer moving relative to the first. Einstein illustrated this with a thought experiment involving a train and lightning strikes. Imagine lightning strikes both ends of a moving train at exactly the same instant, from the perspective of someone standing on the platform. That person sees both flashes simultaneously because the light from each strike has to travel the same distance to reach them. But what about someone sitting in the middle of the train? The train is moving forward. The light from the front strike has a shorter distance to travel to reach them because they are moving toward where that strike occurred. The light from the rear strike has a longer distance to travel because they are moving away from where that strike occurred. The passenger sees the front strike first. You might say, well, that is just because of light travel time. The strikes really were simultaneous, and the passenger is just seeing them at different times. But here is the crucial point. In special relativity, there is no way to determine which observer is really correct. Neither perspective is privileged. The universe does not have a master clock that everyone agrees on. For the platform observer, the strikes are simultaneous. For the train passenger, they are not. And there is no experiment, no measurement, no appeal to some deeper reality that can settle the dispute. This has a far-reaching implication that takes some time to fully absorb. There is no universal now. Different observers moving relative to each other literally live in different versions of the present moment. Let that sink in. There is no single present moment that the entire universe shares. The British physicist Roger Penrose illustrated this with what is called the Andromeda paradox. Imagine two people passing each other on the street. One is walking slowly toward the Andromeda galaxy, roughly 2.5 million light-years away. The other is walking slowly in the opposite direction. Their relative velocities are tiny, maybe 11 miles per hour, but because of the vast distance involved. What counts as now on Andromeda for the first person is different from what counts as now for the second by about several days. One person's now on Andromeda might include aliens debating whether to launch an invasion fleet. The other person's now already has them loading the ships. Same moment on Earth, different events on Andromeda. This is not practically meaningful for anything we do day to day. The distances and speeds involved in daily life are too small for this effect to matter, but it reveals something unsettling about the nature of reality. The present moment is not a single instant shared across the universe. It is observer-dependent. It is relative. The most famous illustration of time dilation is the twin paradox. Imagine identical twins. One stays on Earth. The other boards a spacecraft and travels to a star 10 light-years away at 90% of the speed of light, then turns around and comes home. From Earth's perspective, the journey is straightforward. The star is 10 light-years distant. At 90% light speed, the outbound trip takes about 11 years. The return trip takes another 11 years. Total time elapsed on Earth, roughly 22 years. But from the traveling twins' perspective, things are different. Because of length contraction, the distance to the star is not 10 light-years. At 90% light speed, with a Lorentz factor of about 2.29, the distance contracts to about 4.4 light-years. The trip takes correspondingly less time. Total time elapsed for the traveler, about 9.7 years. When the twins reunite, the traveling twin is approximately 12.5 years younger than the stay-at-home twin. They started the same age. Now one is significantly older than the other. They have experienced different amounts of time. This is not a metaphor or an illusion. The traveling twin really has aged less. Their heart has beaten fewer times. Their cells have divided fewer times. They have literally lived fewer years. This might seem paradoxical. If all motion is relative, why cannot the traveling twin claim that Earth was moving away and returning, which would mean the Earth twin should be younger? The resolution is that the two situations are not actually symmetric. The traveling twin had to accelerate first to leave Earth, then to turn around, then to slow down upon return. The stay-at-home twin remained in a single inertial reference frame the whole time. Acceleration breaks the symmetry, and it is the accelerating twin who experiences less time. Yes, you heard that right. Acceleration, not just speed, is what breaks the tie. This is not a theoretical curiosity. It has been measured experimentally. Actual clocks flown around the world on actual aircraft have returned showing exactly the time differences Einstein predicted. The twin paradox is not a paradox at all. It is simply how the universe works. There is one more fundamental consequence of Einstein's postulates. Nothing with mass can ever reach the speed of light. Here is why. As an object speeds up, its kinetic energy increases. But in relativity, energy and mass are related. The more energy an object has, the more it effectively weighs in terms of resisting further acceleration. As the object approaches light speed, the energy required to accelerate it further increases without limit. Think of it like trying to accelerate a car that gets heavier the faster it goes. At first, pressing the gas pedal makes a big difference. But as you approach some maximum speed, each additional mile per hour requires dramatically more fuel. The car responds less and less to the same amount of force. Eventually, you are burning through infinite fuel just to creep toward a speed you can never quite reach. In the relativistic case, as an object approaches light speed, it becomes effectively infinitely massive, requiring infinite force to accelerate it any further. To accelerate an object with mass to exactly the speed of light would require infinite energy. That is not just a lot of energy. It is an amount that cannot exist. The speed of light is an asymptotic limit that can be approached but never reached. But here is the flip side. Particles without mass must travel at exactly the speed of light. They have no other option. Photons, the particles of light, have no mass. They cannot travel at any speed other than light speed. They are born moving at that speed and never slow down until they are absorbed. Light does not just happen to travel at a certain speed. It travels at the only speed physics allows for something without mass. The speed of light is not arbitrary. It is built into the structure of spacetime itself. Now let us talk about how velocities actually add together at relativistic speeds. In everyday life, velocities add simply. If you are on a train going 50 miles per hour and you walk forward at 5 miles per hour, someone on the platform sees you moving at 55 miles per hour. Straightforward addition. But at relativistic speeds, this simple addition does not work. Here is an example. Two spaceships are approaching each other. From Earth's perspective, each one is traveling at 90% of the speed of light. Common sense says they should see each other approaching at 180% of light speed. But that never happens. Instead, they actually see each other approaching at about 99.45% of light speed. Extremely fast, but still below light speed. The universe has a built-in correction factor that prevents any combination of velocities from ever reaching or exceeding light speed. No matter what you do, no matter how you add speeds together, you will never cross that limit. It is a fundamental law of our reality. Understanding these effects requires thinking about space-time as a unified four-dimensional fabric. We are used to thinking of space as three-dimensional and time as something separate, flowing independently in the background. Einstein showed that they are connected, woven together into a single structure called space-time. The person who did the most to develop this mathematical framework was Hermann Minkowski, one of Einstein's former mathematics professors. In 1908, Minkowski gave a famous lecture that began with these words: "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Einstein was initially dismissive of Minkowski's four-dimensional mathematical formulation, calling it superfluous learnedness. But he later came to appreciate its power, and the concept of four-dimensional space-time became essential to his development of general relativity. One useful tool for visualizing this is the light cone. Imagine a point in space and time representing an event that happens at a specific place and moment. Now imagine all the light rays that could emanate from that event spreading outward at the speed of light. These light rays form a cone shape opening upward into the future. Everything inside that forward cone represents events that the original event could potentially influence. Light or anything slower could travel from the first event to the second. There is also a backward cone representing all events that could have influenced the original event. These are in its absolute past. But here is the crucial part. Everything outside both cones is called elsewhere. Events in the elsewhere region cannot be causally connected to the original event. Nothing can travel between them, not even light. And here is the strangest part. For events in the elsewhere region, different observers will disagree about which happened first. The order of events outside your light cone depends on how fast you are moving. This is why the speed of light is sometimes called the speed of causality. It is the maximum speed at which cause and effect can propagate. It defines the boundaries of what can influence what. It determines what events are in your future, what events are in your past, and what events are fundamentally disconnected from you, existing in a kind of cosmic elsewhere that you can never reach or influence. The light cone also explains why faster than light travel, if it were possible, would create catastrophic logical problems. Imagine you could send a message faster than light. You send a signal to a distant star, and it arrives before light would have gotten there. Now imagine someone at that star is moving relative to you at high speed. Because of the relativity of simultaneity, their now is different from yours. From their perspective, your faster than light signal might have arrived before it was sent. If they then send a reply, also faster than light, that reply could arrive back on Earth before you sent the original message. You would receive an answer to a question you have not asked yet. This is called a causality violation. Most physicists believe that faster than light travel or communication is fundamentally impossible, not just beyond our current technology, but forbidden by the structure of space-time itself. The universe seems designed to prevent causal paradoxes. The speed of light is not just a speed limit, it is a causality limit protecting the logical order of events across all of space-time. Everything we have discussed so far might sound like elaborate theoretical speculation. How do we know any of this is actually true? The answer is we have tested it repeatedly with exquisite precision, and Einstein's predictions have been confirmed every single time. Let us start with the most dramatic, direct test of time dilation, the Haffel-Keating experiment. In October 1971, physicists Joseph Haffel and Richard Keating decided to test the twin paradox with actual clocks. They purchased seats on commercial airline flights and took 4 cesium beam atomic clocks around the world. The eastward trip took place on October 4th, 1971, covering 65.4 hours total, with 41.2 hours of actual flight time. The westward trip occurred on October 13th, lasting 80.3 hours total with 48.6 hours in the air. Why did they fly in both directions? Because the effects of special and general relativity had to be separated. Flying eastward, the planes moved in the same direction as Earth's rotation, increasing their speed relative to the cosmic reference frame. Flying westward, they moved against Earth's rotation, decreasing their effective speed. Additionally, at cruising altitude, the clocks experience weaker gravity than clocks on the ground, which affects time through general relativity. The predictions were specific. The eastward traveling clocks should lose about 40 nanoseconds relative to the ground clocks. The westward traveling clocks should gain about 275 nanoseconds. The results, published in Science magazine in 1972, confirmed Einstein's predictions. The eastward clocks lost 59 nanoseconds, plus or minus 10. The westward clocks gained 273 nanoseconds, plus or minus 7. Both results fell within the predicted ranges. These are tiny time differences, less than a millionth of a second, but they were exactly what relativity predicted, and they represented the first direct macroscopic demonstration that moving clocks really do run slow. The twin paradox is not just a thought experiment, it is reality. The experiment cost only about $8,000, most of which went to purchasing airline tickets. The clocks were given their own seats, and tickets were purchased for them under the name Mr. Clock. It remains one of the most inexpensive yet definitive tests of fundamental physics ever conducted. An even more dramatic demonstration happens every day in particle physics laboratories and even in our atmosphere. Moons are subatomic particles similar to electrons but about 200 times heavier. They are unstable, decaying into other particles with a half-life of about 2.2 microseconds when measured at rest in a laboratory. That is 2 millionths of a second. In the blink of an eye. Literally a muon would undergo thousands of half-lives. Cosmic rays constantly bombard Earth's atmosphere, creating muons about 6 miles up. At 2.2 microseconds per half-life, even traveling at the speed of light, muons should only make it about 2,000 feet before most of them decay. They should not reach the ground in significant numbers, but they do. We detect plenty of muons at Earth's surface. Physicists first noticed this discrepancy in the 1930s and 40s. If you calculate how many muons should survive the trip through the atmosphere based on their rest frame lifetime, you get a number far smaller than what detectors actually measure. The muons seem to be living longer than they should. How is this possible? Time dilation. The muons are traveling at nearly the speed of light. From our perspective on the ground, their internal clocks are running slow. Their 2 microsecond lifetime stretches to many microseconds, giving them enough time to reach us. From the muon's perspective, the explanation is different, but equivalent. They are not living longer than 2 microseconds by their own clocks. But from their viewpoint, Earth's atmosphere is length contracted. The 6 miles they need to cross appears as only a few hundred feet. They easily make the trip in their allotted lifetime. This is beautiful. 2 completely different explanations, time dilation and length contraction, both giving the same answer, and that answer matches what we actually observe. Both explanations are correct in their respective reference frames, and both are consistent with each other. That is what relativity demands, and that is what nature delivers. In 1977, researchers at CERN conducted a precise test using muons in a storage ring. They accelerated muons to 99.94% of the speed of light. The muons experienced extreme acceleration, about 10 to the 18th times Earth's gravity, as they circled the ring. The measured muon lifetime matched the predicted value from time dilation almost exactly. This experiment also confirmed something called the clock hypothesis. Acceleration itself does not affect time dilation. Only velocity does. Despite the extreme forces on the circling muons, their lifetimes match the predictions based purely on their speed. It is not the acceleration that slows time. It is the velocity. Perhaps the most practical everyday confirmation of relativity is the global positioning system. GPS in your phone would not work without relativistic corrections. Every time you use GPS to navigate, you are relying on Einstein's relativity. GPS works by measuring the time for radio signals to travel from satellites to your receiver. Each satellite carries an atomic clock accurate to about 1 nanosecond. By comparing signals from multiple satellites, the receiver can triangulate your position to within a few yards. But here's the problem. The satellites orbit at about 12,500 miles altitude. At that height, they are traveling about 8,700 miles per hour. Special relativity says their clocks should run slower than ground clocks by about 7 microseconds per day because of their velocity. However, at that altitude, gravity is weaker than on Earth's surface. General relativity says clocks in weaker gravity run faster. This effect adds about 45 microseconds per day. The net result? Satellite clocks run about 38 microseconds per day faster than ground clocks. That might not sound like much, but light travels about 7 miles in 38 microseconds. Without relativistic corrections, GPS positioning errors would accumulate at about 7 miles per day. Within 2 minutes, the system would be useless for navigation. The solution is elegant. GPS, satellite atomic clocks, are manufactured to tick at a slightly different frequency than ground clocks. Instead of the standard 10.23 megahertz, they are set to 10.229999543 megahertz. This pre-compensates for the relativistic time difference, keeping the system accurate. Every time you use GPS to navigate, every time your phone shows you where you are on a map, you are relying on Einstein's relativity. If relativity were wrong, GPS would not work. Another early experimental confirmation came from the Pound-Rebka experiment, conducted in 1959 and 1960 at Harvard University. Physicists Robert Pound and Glenn Rebka set up an experiment using a height of about 74 feet. They shot gamma rays from iron atoms at the top of the tower down to a detector at the bottom. According to general relativity, the gamma rays should gain energy as they fall through Earth's gravitational field. This energy gain would shift their frequency slightly higher. The predicted shift was incredibly small, about 2.5 parts in 10 to the 15th power. To measure such a tiny effect, Pound and Rebka used an elegant technique that allows extremely precise frequency measurements. Their results agreed with the prediction within 1%. This was the first laboratory verification that clocks run at different rates depending on their position in a gravitational field. Now let us talk about the practical implications of light's cosmic speed limit, both the technology that depends on it and the constraints it places on our ambitions. We have already discussed GPS, but there is another medical technology that directly demonstrates Einstein's famous equation relating mass and energy. Positron emission tomography, or PET scans, works through matter-antimatter annihilation. A patient receives an injection containing a radioactive tracer. The tracer is unstable and emits positrons, which are antimatter electrons. When a positron encounters an ordinary electron, both particles are completely annihilated. Their combined mass converts entirely into energy in the form of 2 gamma rays. Each gamma ray carries exactly 511,000 electron volts of energy, which is precisely the mass energy of an electron or positron. The gamma rays fly off in exactly opposite directions. PET scanners detect these coincident gamma ray pairs. By tracing the lines between coincident detections, the scanner can pinpoint where the annihilation occurred, mapping metabolic activity in the body. This is Einstein's E equals mc squared in medical action. Every PT scan performed in hospitals around the world is a demonstration that mass and energy are equivalent. At the other extreme of energy, the Large Hadron Collider at CERN accelerates protons to speeds where relativistic effects dominate completely. The LHC is a ring about 17 miles in circumference, buried beneath the border between Switzerland and France. Protons circle this ring 11,245 times per second, traveling at 99.999991% of the speed of light. They are moving just about 10 feet per second slower than light itself. At this speed, the protons have roughly 7,460 times their rest mass in kinetic energy. From the proton's perspective, the entire 17-mile ring appears to be only about 13 feet around, contracted by relativity. When protons traveling in opposite directions collide head-on, the collision energy is enough to create particles that are thousands of times heavier than protons. Particles that have not existed naturally since the first moments after the Big Bang. The Higgs boson, discovered at the LHC in 2012, has a mass of about 125 billion electron volts, more than 100 times the proton's rest mass. That mass is created purely from the collision energy. Energy becomes matter, exactly as Einstein's equation predicts, but the speed of light also imposes harsh limits on what we can do. And this is where the implications become sobering. Consider communication with spacecraft. Light travels at 186,000 miles per second. That sounds incredibly fast, but space is vast. The moon is about 239,000 miles away. Light takes 1.3 seconds to make the trip. A round-trip communication takes 2.6 seconds. This was manageable during the Apollo missions, though it made conversation slightly awkward. There's always that pause, that lag audible in the mission recordings. Mars is much farther. At its closest approach to Earth, it is about 34 million miles away. Light takes about 4.3 minutes to cross this distance. A round-trip message takes at least 8.6 minutes. At its farthest, when Mars is on the opposite side of the Sun, the distance grows to about 250 million miles. One-way light travel time stretches to about 24 minutes. You ask a question, and the earliest you can possibly receive an answer is 48 minutes later. This is not a technology problem we can solve with better radios. It is a fundamental feature of spacetime. The speed of light cannot be exceeded, so communication delays cannot be eliminated. The Voyager 1 spacecraft, launched in 1977, is now about 15.6 billion miles from Earth. Light takes about 23.5 hours to reach it. A command sent today will not arrive until tomorrow. By the time you hear this, Voyager 1 may already be more than one light day away. And Voyager 1 is still within our solar system's outer reaches. The nearest star system, Alpha Centauri, is about 4.24 light-years away. That is roughly 25 trillion miles. Any message we send would take more than 4 years to arrive. A conversation spanning 8.5 years between exchanges is barely a conversation at all. The cosmic speed limit also determines what we can see. The universe is about 13.8 billion years old. Light that started traveling toward us 13.8 billion years ago has had that long to make the journey. This defines the edge of the observable universe. The most distant light we can receive is 13.8 billion years old. But here is where it gets counterintuitive. The observable universe has a radius of about 46.5 billion light-years, not 13.8 billion. How can we see objects farther away than light could travel in the universe's lifetime? The answer is that space itself has been expanding. Light that started its journey 13.8 billion years ago was much closer then. As it traveled, space stretched. The source of that primordial light has continued receding. By now, those early objects are 46.5 billion light-years away. The observable universe is therefore about 93 billion light-years in diameter. Beyond that boundary, light has not had time to reach us. There may be vastly more universe beyond what we can see, but we have no way to know. Even stranger, distant galaxies are receding from us faster than the speed of light. A galaxy beyond the so-called Hubble horizon, roughly 14 billion light-years away, is being carried away from us by the expansion of space at a rate exceeding light speed. This does not violate relativity. Special relativity says objects cannot move through space faster than light. It says nothing about space itself expanding. The galaxies are not flying through space at superluminal speeds. Space itself is stretching, carrying them along. Light from those galaxies emitted now will never reach us. They are beyond our cosmic horizon forever. We are fundamentally, irreversibly cut off from those regions of the universe. Given how restrictive the light speed barrier is, it is natural to ask, is there any way around it? Scientists and science fiction writers have explored various possibilities. Most turn out to be impossible, but a few remain tantalizingly open questions. Let us start with what definitely does not work: quantum entanglement. When two particles become entangled, measuring one instantly affects what you will find when measuring the other, regardless of distance. Einstein called this spooky action at a distance and never fully accepted it. In 2022, the Nobel Prize in Physics was awarded to 3 scientists for experiments with entangled photons. Many people hear about entanglement and think it could enable faster-than-light communication. It cannot. Here is why. When you measure an entangled particle, you get a random result. You cannot choose what outcome you will get. And neither party can tell whether the other has made a measurement. The correlations between entangled particles only become visible when you bring the measurement results together and compare them, which requires normal light speed or slower communication. The spooky action creates correlations, not signals. Quantum mechanics, despite its weirdness, respects the speed of light. What about hypothetical particles that travel faster than light? In 1967, physicist Gerald Feinberg coined the term tachyon for such hypothetical particles. Tachyons would always travel faster than light, and adding energy would slow them down. The problem with tachyons is causality. If tachyons existed and could be used to send information, they would enable signals to be received before they were sent in certain reference frames. No tachyons have ever been detected. Most physicists believe they do not exist. A more interesting possibility comes from general relativity, the Alcubierre warp drive. In 1994, Mexican physicist Miguel Alcubierre showed that Einstein's equations permit a configuration of spacetime where a bubble of flat space could move faster than light relative to distant observers. The bubble would not be moving through space at superluminal speeds. Instead, space itself would be contracting in front of the bubble and expanding behind it. The ship inside the bubble would be locally stationary while the bubble carried it along. This technically does not violate special relativity. The catch is that creating such a bubble would require what physicists call exotic matter, matter with negative energy density. In ordinary physics, energy is always positive or zero. Negative energy density would require something unlike any known material. Initial calculations suggested the energy requirements were astronomical, equivalent to the mass of Jupiter converted entirely to energy. Later work showed that changing the bubble shape could dramatically reduce the requirements. But dramatically reduced still means far beyond any technology we can imagine. Wormholes represent another theoretical possibility. These are solutions to Einstein's equations that connect 2 distant points in spacetime through a shortcut. The original Einstein-Rosen bridges are non-traversable. They collapse too quickly for anything to pass through. Later work showed that stabilizing a wormhole large enough to pass through would require negative energy equivalent to the mass of Jupiter. If wormholes could be created and stabilized, they would raise the same causality concerns as any faster than light travel. There is one way to exceed the speed of light that is completely real and does not violate any physics: traveling faster than light in a medium. Light travels at 186,000 miles per second in a vacuum, but in other materials, it travels slower. In water, light moves at about 75% of its vacuum speed. In glass, about 67%. In diamond, only about 41%. A charged particle moving through water faster than light moves through water creates an electromagnetic shock wave similar to a sonic boom. This phenomenon is called Cherenkov radiation, and it produces a characteristic blue glow. If you have ever seen photographs of nuclear reactor cooling pools, you have seen Cherenkov radiation. The water glows an eerie blue because electrons from nuclear reactions are traveling faster than light travels in water. This does not violate relativity because the fundamental limit is the speed of light in vacuum. Particles can exceed the local speed of light in a medium while still traveling well below the vacuum speed of light. Sometimes things in space appear to move faster than light without actually doing so. Astronomers observing certain quasars have measured apparent velocities exceeding 10 times the speed of light. These are optical illusions created by geometry. When a jet of material moves at nearly the speed of light in a direction partly toward Earth, the light travel time from different points along the jet gets compressed in an unintuitive way. The jet appears to cover more angular distance than it actually does. The true speed is still below light speed. One more striking phenomenon deserves mention. In 1999, Danish physicist Lene Hau achieved something that sounds impossible. She slowed light down to 38 miles per hour. Her technique involved passing light through an ultra-cold state of matter called a Bose-Einstein condensate. In this exotic state near absolute zero, the interaction between light and matter becomes extreme enough to bring light almost to a standstill. 38 miles per hour is 20 million times slower than light travels in vacuum. Later, Hau went further. She stopped light completely, holding it in place for a measurable time, before releasing it to continue on its way. These experiments do not violate relativity. The fundamental speed limit is light in vacuum. What Hau demonstrated is that the interaction between light and matter can be manipulated to produce astonishing effects. But even stopped light in a Bose-Einstein condensate is not violating any laws. The cosmic speed limit remains intact. Let us step back and consider what the speed of light means for our place in the universe. We live in a cosmos of staggering size. The observable universe spans about 93 billion light years, but everything beyond our cosmic neighborhood might as well be unreachable. Light from the sun takes 8 minutes and 20 seconds to reach Earth, crossing 93 million miles. We see the sun as it was 8 minutes ago. If the sun suddenly went dark, we would not know for over 8 minutes. The nearest star to our sun is Proxima Centauri, 4.24 light years away. That is roughly 25 trillion miles. Light takes more than 4 years to make the journey. Even if we could build a spacecraft traveling at 10% the speed of light, which is far beyond current technology, the trip would take over 40 years each way. The Milky Way galaxy spans about 100,000 light years. Crossing from one side to the other, even at the speed of light, would take longer than modern humans have existed as a species. The Andromeda Galaxy, our nearest large galactic neighbor, lies 2.5 million light years away. The light we see from Andromeda left when our ancestors were still developing the first stone tools. Any civilization in Andromeda looking at Earth now sees a planet without humans. This creates a peculiar kind of cosmic isolation. We can see the light from billions of galaxies, but we can never visit them, never communicate with anyone who might be there, never receive a reply within any human lifetime or any 1,000 human lifetimes. The speed of light also shapes what we can know about the universe. Because light takes time to travel, looking at distant objects means looking back in time. When we observe a galaxy 1 billion light years away, we see it as it was 1 billion years ago. Telescopes are time machines, but it also means we can never see the universe as it currently is. Our view is always a composite of different ages, more recent nearby and more ancient farther away. There are events happening right now in distant galaxies that we will never see because the universe's expansion is carrying those galaxies away from us faster than light. Light emitted by those galaxies today will never reach us. We are forever cut off from most of the universe's current state. The cosmic speed limit also affects the search for extraterrestrial intelligence. If an alien civilization exists on a planet orbiting a star 100 light years away, any signal they send us takes 100 years to arrive. Any reply we send takes another 100 years to get back. A single exchange takes 2 centuries. If the civilization is 1,000 light years away, still within our own galaxy, a back and forth communication spans 2,000 years. The Roman Empire would have needed to start the conversation for us to be receiving replies now, and 1,000 light years is practically next door on cosmic scales. This creates what some scientists call the Great Silence. Even if the galaxy is teeming with intelligent life, the vast distances and the speed of light might make contact essentially impossible. 2 civilizations might exist simultaneously in the Milky Way, both searching for each other, both sending signals into the void, and never connect because their signals have not had time to cross the intervening space. This isolation might be the natural state of intelligent beings in the universe. Not because we are alone, but because the cosmic speed limit creates unbridgeable gulfs between stars. Every civilization might be an island, visible to others through telescopes, but forever beyond reach of conversation or visit. If that is true, then the speed of light is not just a physical constraint. It is a fundamental feature of existence in this universe, a kind of cosmic loneliness built into the structure of space-time. The speed of light does not just constrain what we can do, it challenges the deepest assumptions we have about the nature of reality. And these are not abstract philosophical puzzles. They are direct consequences of experimental facts. Think about what we have established. Time genuinely runs slower for moving objects. Space genuinely contracts. Events that are simultaneous for one observer are not simultaneous for another. These are not approximations or simplifications. They are how the universe actually works. But if that is true, then many of our basic assumptions about reality must be wrong. We naturally think of time as a river flowing at a constant rate, carrying us all forward together. We think of space as a fixed stage on which events play out. We think of now as a single moment that everyone shares, spreading across the entire universe at once. Relativity tells us none of this is true. Consider what the relativity of simultaneity really means. If there is no universal now, if different observers legitimately disagree about what is happening at this moment in distant places, then what is the present? Einstein himself took a radical position on this question. He came to believe in what philosophers call the block universe, or eternalism. In this view, past, present, and future all exist equally. Space-time is like a four-dimensional block of ice with all events frozen in place. Our experience of now moving through time is an illusion, a peculiarity of consciousness, not a feature of physics. Einstein expressed this view most movingly after the death of his lifelong friend Michel Besso in 1955. Einstein wrote to Besso's family, "Now, he has departed from this strange world a little ahead of me. That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion." Einstein died just weeks later. If his block universe view is correct, Besso and Einstein both still exist, frozen in the space-time of their lifetimes, as real as any moment we call present. Now, if that is true, then this forces us to ask a disturbing question. If now depends on who is looking, then in what sense does the present moment actually exist? Is the future already out there, waiting for us? Is the past still real, somewhere? These are not just idle questions. They are direct implications of the fact that the speed of light is finite and constant for everyone. Not all philosophers accept the block universe conclusion. Some argue that there are ways to recover a meaningful present moment even in relativity, perhaps by privileging a particular reference frame, or by accepting that reality is perspectival. These debates continue in philosophy departments and physics conferences around the world. The honest answer may be that we simply do not know yet. The relationship between physics and the fundamental nature of reality remains one of the deepest unsolved problems in philosophy. What we can say is that the speed of light forces us to take these questions seriously. It is not just speculation. The experimental facts demand that we revise our intuitive picture of time and space. Another philosophical puzzle concerns the nature of the speed limit itself. Why is the speed of light what it is? Why 186,282 miles per second rather than some other number? The answer, as far as physics can tell, is that it simply is. The speed of light is a fundamental constant of nature, not derivable from anything more basic. It appears in the equations of physics as a given, not as a consequence. Some physicists have speculated about varying the speed of light to see what would happen. A universe with a different value would have different chemistry, different stellar physics, different everything. In most such universes, complex structures like atoms and life could not exist. Our universe happens to have a speed of light compatible with our existence. This observation leads some to anthropic arguments. Perhaps there are many universes with different constants, and we necessarily find ourselves in one compatible with observers like us. Others find such arguments unsatisfying, hoping for a deeper explanation. For now, the speed of light remains a mystery at the deepest level. We know what it is. We know how it shapes physics, but we do not know why it has the particular value it does. Throughout this journey, we have traced humanity's 400-year effort to measure the speed of light and understand its consequences. Let us bring it all together. In 1676, old Rømer watched Jupiter's moons and realized that light takes time to travel across space. His calculation was off by about 25%, but he proved the essential truth. Light, however fast, is not instantaneous. It took 53 years for Bradley to independently confirm this discovery. Over the next 2 centuries, Fizeau, Foucault, and Michelson refined the measurements with increasing precision. By 1887, Michelson and Morley had shown that light travels at the same speed in all directions regardless of Earth's motion. The ether did not exist. Something strange was going on. In 1905, Einstein explained what? He accepted the constancy of light speed as a fundamental feature of nature and showed that time and space must be flexible to accommodate it. The resulting theory of special relativity revealed that moving clocks run slow, moving objects shrink, and simultaneity is relative. In the decades since, every prediction of relativity has been confirmed experimentally. Atomic clocks flown around the world show exactly the time differences Einstein predicted. Particles in accelerators live longer than they should because their time runs slow. GPS satellites require constant relativistic corrections to function. The equations are not just mathematically elegant, they are the accurate description of how reality works. The speed of light is not merely an interesting constant, it is woven into the structure of spacetime. It connects mass and energy through Einstein's famous equation. It defines the boundary between what can influence what. It determines what we can see and what remains forever hidden. And it poses limits that we may never overcome. We can approach the speed of light but never reach it. We can look at distant galaxies but never visit them. We can send messages to the stars but never expect a timely reply. Some find this depressing. The universe is vast and mostly unreachable. Even our nearest stellar neighbors are effectively isolated from us by the tyranny of light speed. But there is another way to see it. The speed of light is not just a barrier. It is a window into the deepest structure of reality. It teaches us that space and time are not the fixed stage we thought they were, but flexible, interconnected, responsive to motion and gravity. It shows us that mass and energy are 2 faces of the same coin. It reveals that causality itself has a speed limit, preserving the logical order of events across the cosmos. For thousands of years, humans assumed that time flows uniformly, that space is absolute, that distance is the same for everyone. The speed of light showed us that none of these assumptions are true. Our everyday intuitions, evolved on a small planet at walking speeds, simply do not apply to the larger universe. Understanding this does not diminish our place in the cosmos, it deepens it. We are creatures who evolved to see the world in simple terms, and yet we have developed the tools, mathematical and experimental, to perceive truths far beyond our sensory experience. We cannot feel time dilation, but we can measure it. We cannot see length contraction, but we can calculate its effects. We cannot travel at relativistic speeds, but we can understand what would happen if we did. If this exploration of the cosmos made you see the universe a little differently, please like this video and subscribe for more deep dives into physics. It is a small thing for you, but it makes a huge difference for this channel. In 1946, near the end of his life, Einstein reflected on that thought experiment that had troubled him since he was 16 years old. What would it be like to chase a beam of light? He never did get to ride alongside a light beam. No one ever will. But in trying to answer that question, he discovered something deeper than any journey could reveal. He discovered that the universe is stranger, more subtle, and more beautiful than anyone had imagined. The speed of light does not just tell us how fast light travels. It tells us what kind of universe we live in. And that universe, it turns out, is far more interesting than the simple, intuitive one we thought we knew. So the next time you look up at the stars on a clear night, remember what you have learned tonight. Those points of light scattered across the darkness are not just lights. They are distant suns, massive balls of fusing hydrogen, each one potentially hosting its own system of planets and moons. They are light years away, separated from us by distances so vast that the light entering your eye right now has been traveling for years, decades, centuries, or even millennia. Some of that light began its journey before you were born. Some of it left its star before your grandparents were born. Some of it has been traveling since before there were any humans at all. You are connected to those distant stars across the vast distances of space and time, linked by photons that have crossed the cosmic void to reach you. The universe is large beyond comprehension. You are small, a single person on a single planet. But you are here, and you can understand, at least conceptually if not intuitively, what the speed of light really means. You can grasp that the universe is measured in these vast units, that space is filled with distances that dwarf anything in human experience. And that understanding, that ability to comprehend your place in the cosmos, is something worth holding on to. The speed of light is 186,282 miles per second. It is a number, precise and exact, now fixed by definition. But what that number represents, the cosmic speed limit, the boundary of causality, the weaver of spacetime, is something far grander than any number can convey. The speed of light breaks our everyday reality. But in doing so, it reveals a deeper reality, one where time bends, space shrinks, and the cosmic speed limit preserves the order of cause and effect across all of creation. That is not a limitation. That is a revelation. Until next time, keep looking up.